6.7, recursively defined sequences. Okay, so we've been dealing with formulas for sequences that are called explicit formulas. And explicit formulas, you plug in the term number to find any term value. Term number is the blank there, okay? So on this example here, I'm trying to find a sub 10. That means I'm trying to find the 10th term in this sequence. So when I want a sub 10, I just plug in 10 for into the equation. So I've got 4 times 10 minus 2, okay? And then I simplify that. So let's see, I do the multiplication first. I've got 40 minus 2, which is 38. So that's the 10th term in that sequence. That's called an explicit formula because it gives you an explicit term. So I could find the 100th term just by plugging in a 100 where the 10 is, right? Or any term, okay? A recursive formula is something different. A recursive formula depends on the previous term. Okay, it's built on the previous term. So let's look at one of these. Okay, on this example, this is going to be a recursive formula, and I'll show you why in a second. So if I'm using the same strategy, I'm supposed to find the first 5 terms. Well, I've got the first one already, right? So there's one of them. Hey, that's nice. I was given that one for free. So let's just say, okay, there's the first one. So let's find the second term. And I can use the same technique I used in the previous problem. I can just plug in 2 for n. So I've got 2 and a, and then the little footnote part, I'd have 2 minus 1. Okay? And then when I start to simplify that, I've got 2 times a sub 1. Okay? Now, I would be stuck here if I didn't already know that a sub 1 equals 3. Okay, that's why they gave you the first term, because you're always going to need a term to build off of. So in this case, a sub 1 equals 3, and that means I know that second term is going to be 6. Okay, and let's find the third term. Now, it turns out when you have a sub n minus 1, what we did here is we took 2 times the previous term, right? So this a sub n minus 1 always comes out to be the previous term. Because let's say you were looking for the 100th term. Well, you plug in a 100 for n, and that means this would be a sub 99 once you subtract the 1 from the 100. Okay? So whatever term you're looking for, it's going to be the previous term. So when I look at this, I just think, oh, it's 2 times the previous term. You could go through with plugging in the n every time like I did on to find the second term, but I'm just thinking, okay, 2 times the previous term. My previous term, when I'm looking for the third term, is going to be 6. So then 2 times 6 is 12. Okay, and then when I'm looking for the fourth term, 2 times the previous term. I'm going to do the same thing for the fifth one, 2 times the previous term. It's just the previous term is going to keep changing as I go down the line. So when I'm looking for the fourth one, my previous term is 12. 2 times 12 is 24. And then when I'm looking for the fifth one, my previous term is 24, so that's 48. Okay, and now I've got the first 5 terms, right? You could write them like this, or you could write them as a list in a sequence. You could say, let's see, I'll write them as a list as well. I've got 3 is my first term, 6, 12, 24, and 48. So you could write them that way if you like. Okay. All right, so now we're going to graph this this recursive sequence here. Okay, so we've got the term numbers here. The first term was 3, so my first term, the value of that first term is 3. Okay, second term is 6. The third term is 12, then 24 and 48. Okay, and let's plot these and see what happens. So we've got the point 1, 3. So it's a little hard to see here, but I'm going 1 to the right, 3 up. There it is. And then 2, 6. It's right there. 3, 12. 4, 24. And 5, 48 is in that top right corner. Okay? So hopefully you can see we're going to get, this looks like an exponential curve. And it is an exponential curve. They fit on an exponential curve because this is a geometric sequence. We're multiplying by one thing to get from one term to the next, right? We're doubling the y values when the x values are evens or even. Okay, so if you kept plotting more of these points, you're going to get an exponential curve, something like that. Okay. All right, let's try another of these. So I'm looking at this one, and I'm seeing a sub n minus 1. So I'm thinking to myself, oh, that's going to be my previous term. Okay, so I've already got the first term is 2. So let's find the second term. When I'm looking for the second term, I'm going to do this previous term plus 3. So I like to kind of just set these all up right off the bat. It's always going to be the previous term plus 3 for each of these. Okay. All right, so 2 is my first term, so that means when I'm looking for the second one, 2 is the previous term. 2 plus 3 is 5. So it's a chain reaction, right? And then I put the 5 in here. 5 plus 3 is 8. Then I'll put the 8 in this slot. 8 plus 3 is 11. And 11 plus 3 is going to be 14. So it goes pretty quickly once you get the hang of once you realize that that just means the previous term. If you set up the skeleton, you can just plug the numbers in pretty quickly. Okay, so I'm going to graph these like I did on the last problem. I've got my first 5 terms. The first term was 2. Second term, 5, 8, 11, and 14. Okay, and let's graph these. I've got 1, 2 here, 2, 5, 3, 8, 4, 11, and 5, 14 is in the top right corner there. Okay, this one looks like it's lined up in a straight line, and that makes sense because on this one, it's a linear term. We're adding to get from one term for the y's, or adding to get from one term to the next, but on the xy table with those, right? As opposed to this one where we're multiplying by 2 to get from term to term. So when you're multiplying, you get a geometric sequence, which is going to be a curve. But when you're adding to get from term to term, that means you've got a common difference. And that means your points should be lined up on a straight line. Something like that. Okay. Let's look at some generic equations then on the next page. So we've got some arithmetic sequence equations and some geometric sequence equations. So the common the D is going to be the common difference for the arithmetic ones. Like I was talking about on the last page, we're adding the same thing to get from term to term when we've got an arithmetic sequence. And then R is going to be the common ratio when we're working with a geometric sequence. So we're multiplying by the same thing to get from term to term. Okay, so we've got our explicit, our arithmetic sequence explicit equation. So the two at the bottom here, we've seen these before, right? We're using the difference here and the ratio here, and then you can get any term you want. You can get the 76th term if you know what the first term's difference are. You just plug in 76 for n, right? These ones are different because we've got the a sub n minus 1 in both of these. So remember, this is going to be previous term. And the same thing over here, right? This is our previous term. Okay. So these ones are a little different, but it makes sense. You're taking a previous term and adding something to it to get to the next term. Here you're taking your previous term and multiplying it by something to get from term to term. Okay. All right. So let's talk about how to write a recursive rule. A recursive rule just means we're going to write one of these equations. A rule is just an equation. Okay. All right, so what we want to do is figure out first off if it's arithmetic or geometric. That's important because it's going to determine which of these two equations we're going to use. Then we need to find either the common difference or the common ratio, depending if it's arithmetic or geometric. Okay, and then we can write the rule by substituting in the difference or ratio into one of the equations. All we really need here, our answers are going to look something like this. A sub n equals 7 times a sub n minus 1, something like that, if we're multiplying by 7 to get from term to term. Or we might have a sub n equals a sub n minus 1 plus 13 if our difference is 13 for an arithmetic one. So all we need to figure out is this piece and plug it in, okay? So let's try it out. So first I'm just looking for a pattern. I'm just looking at this and thinking, am I multiplying by the same thing to get from term to term or adding? And in this case, it looks like the numbers are getting smaller. You can't really, it's not going to work with multiplication. To try to find a ratio, you can always take a term and divide by the previous term. So 3 divided by 8 is 0.375. That means 8 times 0.375 equals 3. But then if you try to multiply by 0.375 again, it's not going to get you to the next term. It doesn't get me to -2. So multiplication's out. So then I'm looking for a difference. And these are going down, so we're subtracting, right? So we're going to be subtracting 5, which is the same as adding -5. So we can consider that adding the same thing, getting from term to term. You can also take any term like the 3 and subtract the previous term to get the difference. And then that's going to work all the way down the line. You're going to get the same thing from term to term. Okay, so this one is arithmetic. Okay, so I'll just put that. So I just need to keep that in mind. That means I'm going to be using the recursive. Zoom out here a little bit. The recursive arithmetic equation. So I'm using a sub n equals a sub n minus 1 plus d. Okay. It's really important that the n minus 1, if it's supposed to be a footnote, that it is there. Because if you wrote it a sub n minus 1 without the n minus 1 small and down at the bottom, it would mean something different, right? But all I have to do then is plug in the d, which I've already found. The d is the difference. It's -5. So I'm going to write it like that. Okay, so it's always going to be my previous term minus 5 to get from term to term. And it works here, right? You can try it out. If you wanted the first term, well, I guess the first term you'd have to plug in a 2 here to get the first term. But it's going to subtract from 5 to get from term to term. Okay, looking at this next one, let's see if we can do this with adding. So I'm thinking, okay, I would add 1.3 to get from 1.3 to 2.6, but then if I add another 1.3, well, that will put me at 3.9. So this looks like this is addition again. Okay, so I'm adding 1.3. For a second I thought that it was going to be multiplying by 2, but 2.6 times 2 isn't 3.9. So this one is going to be arithmetic again. Okay, so we're going to use that same formula we did on the previous problem. And I just put in 1.3 for the difference. And there we go. Okay. All right, this next one, 4 to 20, if we're adding, we're going to have to add 16, but then we're definitely not adding 16 to get from 20 to 100. So this one is going to be a multiplication one. Okay, so 4 times something is 20, that would be times 5. 20 times 5 is 100, 100 times 5 is 500, and so forth. So it does work multiplying by 5. So this one is geometric. Okay, so from the top of the page, I got to choose that other recursive equation. That's going to look like this. Okay, so all I have to do here is plug in the ratio. Ratio is 5, already found that. You could write this without the little dot because 5a sub n minus 1 would mean also where you're multiplying. But either way, it doesn't matter. Okay. And then this next one, let's see, 7 times something is 16. Well, that's not going to be an even number, but let's just try it out. Let's see what our ratio is going to be to get from 16 to 7. So I'm going to take, or 7 to 16, I'm going to divide. Okay, it's like 2.2857, something like that. But if I take 16 times that number, let's see if that's going to get me to 25. And it doesn't. Okay, so it's not working with multiplication. So then I'm going to look for a common difference. So I'm thinking 7 plus something is 16. That would be 9. And 16 plus something is 25, also 9. So then I'm thinking, okay, let's keep adding 9 all the way down, and it works to generate all those numbers. So this one is going to be arithmetic again. Okay, so I'm using the arithmetic formula and plugging in the difference, which I already figured out was 9. Okay. Okay, on the last page, we're going to translate back and forth from explicit to recursive rules. All right, and the process is pretty similar. So you need to figure out if we're dealing with arithmetic or geometric, and then we're based on that, we're going to find the common difference or the common ratio, and then we'll substitute into one of the formulas. Okay, so you could always build out a couple of terms, but if you get used to looking at this, this means, hey, this is going to be the previous term plus something. So it means we're always going to add 20 to get from term to term. So for that case, just looking at this formula, I'm seeing that this is going to be arithmetic. Okay? So it says write an explicit rule for this recursive rule. So this is a recursive rule, but I want to write an explicit rule from it. So that means I'm going to go get out the explicit formula for arithmetic. So from that last page, so you can see how this is in that same format, right? The 20 just in place of the D. So I'm going to get out the explicit formula then, which looks like this. Okay. And then I need to substitute in the difference. So if you know where to look, this is going to be the difference. So then I'm just going to put a 20 there. Okay, and I'm also, sorry, I need to plug in both of these things. The first term is negative 45, and then the difference is going to be 20. Okay. And you could leave your answer like this, or you could simplify this. I think I'm going to simplify it a little bit. So I'm going to write it without parentheses by distributing. Okay, so I've multiplied both those pieces by 20, and now I'm going to combine my like terms. So I've got 20n, and then negative 45, and negative 20 is negative 65. So I'm going to write my answer like this. Okay? And that means now I've got an explicit formula. If I wanted the 300th term, all I have to do is plug in 300 for n. You can find any term quickly with an explicit formula. Okay? So if you had trouble telling that this was arithmetic, build out a couple of terms. We got the first term. You could find the second term by doing negative 45 plus 20, and then you could do a chain reaction thing to build a couple of terms. And that might help you to see what the difference is as well. So that's another method if you didn't recognize that this is arithmetic. Okay, if you do recognize what type you have, you can just pick out the pieces. Okay, so that's what I'm going to do in the interest of time here. So let's look at this next one. So I'm trying to decide if this is arithmetic or geometric. So I'm looking at this formula. It's something times n minus 1. Well, that would be in this format, right? So this one is going to be geometric. And this is going to be my ratio, right? The ratio is negative 3. Okay, so that's all I really need. So, whoops, I should keep this out. So now that I know it's geometric, I'm going to pull out the explicit equation, which is a sub 1 times r to the n minus 1. Okay, and I'm going to substitute into the explicit equation for geometric. So I'm going to substitute in the first term and the ratio, and I have both of those things. The first term is 13. And then the ratio is negative 3. Okay? It's really tempting to think, oh, hey, I can multiply 3 times negative 13 to. I see a lot of times that people will simplify this and say, okay, this is negative 39 to the n minus 1. But it's not. because you have to follow PEMDAS. You'd have to do the exponent before the multiplication, and I can't really do the exponent because I don't know what n equals. Okay, so this is as far as you can simplify that. But again, you could find the 100th term now just by plugging 100 in for n, and it's not, now that it's explicit, this isn't built on the previous term. I don't need the previous term to find any term. So that's the idea there. Okay. All right. So now let's work in the other direction. All right. So let's just to show you the other method, let's just build a couple of terms, since this is an explicit one, and I'm going to be writing a recursive rule from this. So I've got negative something plus 1. The something is going to be the term number, okay? And then so when I'm finding a sub 2, something plus 1. Same thing with a sub 3, something plus 1. The something here is the n, so that's 2, this is 3. You really only need 3 terms to figure out if it's arithmetic or geometric, so I'm just going to go with those. So let's see, this is negative 1 plus 1 is 0. Negative 2 plus 1 is negative 1. Negative 3 plus 1 is negative 2. So now I've got 0, negative 1, negative 2, and we could build more terms, but now we can figure out, okay, I'm subtracting 1 to get from term to term, right? So now I know that this is arithmetic. Okay, that's important. And then my difference is going to be negative 1, right? That's what I'm subtracting or adding to get from term to term. I'm adding negative 1, okay? So now, since I'm going to write a recursive rule, I need to find the recursive arithmetic equation. And the recursive one for arithmetic looks like this. Okay, and all I have to do here is plug in the d. And the difference is negative 1. And there we go, okay? And so, you know the first term's 0, so you can try it out. If you plugged in 0 and then subtracted 1, that would get you to negative 1. If you plugged in negative 1 for your previous term, that would come out to negative 2. So it'll work to create that this sequence here, right? Okay, let's try it again. You might recognize this because you have the n minus 1 as an exponent. This one's going to be geometric. But again, if you weren't sure, build a couple of terms, build 3 terms. Okay, let's see. 1 minus 1 for my exponent there is going to be 0. Okay, anything raised to the 0th power equals 1. So then that first term is 2.55. Let's find the second term. So I've got here negative 2.5 times 4 to the first. Well, 4 to the first is just 4. And then, let's see, negative 2.5 times 4 is going to be negative 10. 4 quarters is $1, right? So 2.5 times 4 is 10. So I get negative 10, and then negative 2.5 times 4 to the 3 minus 1. That's going to give me negative 2.5 times 4 to the second. Well, 4 to the second is 16, doing the exponent. And then the multiplication, negative 2.5 times 16 comes out to negative 40. Okay, so now I got 3 terms to work with, and I can play around with this and try to figure out if it's arithmetic or geometric. Let's see, those first 3 terms are these. Okay, and so I've got a way bigger gap between negative 10 and negative 40 than I do between these two. So it's not going to be adding. I'm not going to be adding the same thing. So let's look at multiplication then. Okay, so negative 10 times something equals 40. Well, I know that's going to be 4. Right? Negative 10 times 4 is 40. So let's see if that works with the negative 2.5. Negative 2.5 times 4 equals negative 10. So this is also 4. Okay? And if you know where to look, if you think about the explicit formula, that this is going to be the ratio. So if you recognize that, that works too. Okay? So this one now I know it's geometric. So I'm getting out my specific term formula for, or sorry, my recursive term formula for geometric, which is going to be a sub n equals r times a sub n minus 1. And all I have to do here is plug in the ratio, which is 4. So I've got 4 times a sub n minus 1. And I've got my recursive geometric sequence there. Okay? All right, that's the end of the section, and I'll see you next time.